Before we continue the discussion of actual randomized algorithms, I'd like to take a step back and for one, it's kind of 2 steps back. I'd like to properly define what it means if a randomized algorithm runs and has a certain running time where the possibility is that it doesn't ever finish. This is something we'll be confronted with, and we'll have to find some proper solutions for that. And to properly handle randomization in general, and this particular problem in particular, we'll need some background from probability theory. Much of this will be repetition from some kind of, most computer science curricula have some probability theory in them. They may differ in how formal they get. And so most of it will be repetition. I didn't want to include more than necessary, but really there was this one bit where we need a little bit of a more abstract view on probabilities. Okay, so without further ado, we'll revisit some key terms, also to make sure the terminology is known to everyone, also the English terms, and have a place to look up notation. As always in computer science, we'll mostly deal with discrete things, but it turns out we can't fully avoid continuous or more general probability spaces. And sometimes continuous is just a convenient way to analyze things, even if the underlying process is discrete. So what's this all about? If you want to formally speak about probabilities and what does it mean that something is random, and how can you quantitatively make statements about it? The first thing is you want to settle for some framework where you can assign things a probability. And that's what a probability space is about. The easiest case is the discrete case. You have some ground set. These are the things that can happen at the basic level. Let's do a concrete example. A fair die, standard 6-sided die, no fancy role play things. Then the possible outcomes are just the number of, let me draw it like a graphical way just to make sure that these are effectively arbitrary objects, and that's not a nice 5. So let's represent these as like abstract symbols. We're also in the city of the blind, so it's almost looks like Braille, but of course it's not because it's 3 columns. But okay, just some abstract objects. I guess I should have drawn some shapes around this to make it even nicer. So this is the different sides that a 6-sided die, a cube, can come up with. That's the underlying event space, or do we have a name for omega? Does anyone know? It's just the basic events, I think. Well, that's the one thing. So you have to say in a random process, what is the possible things that can happen? And then the second important bit is we have to assign them probabilities. That's the whole purpose of this. And so I'll always denote probability by this double stroke blackboard font P, just to have it a little shorter than spelling out probability or something like that. In principle, this is just a function. In the discrete case, it maps subsets of our ground set to probabilities. But really, it's determined by giving the individual elementary events some probability weight. And so here, in the case of our fair die, we would say the probability of each of those is just 1/6, if it's a fair one. Okay, I already regret drawing this in different colors. Just as one example, of course you can, in this case, let's define it for all of the faces to be 1/6. That's a fair die, but you could also have a kind of cheating die where maybe the 6 comes up more often. Once you defined for the elementary outcomes what the probability is, you just sum up. If you have a larger set, in the general case, we have a set of these, and you just sum up the weights. That's super boring and trivial, right? So the reason why I spelled this out is to contrast it to the general case. Not everything is discrete. Now here already things are not necessarily finite. My example with the die was finite. Omega is a fixed size, but it could be a countably infinite set. That's all right. But we would still call this discrete because you can bijectively map it to natural numbers. That's what countable means. But that's not all there is. If you want to talk about real numbers, then trouble already starts brewing. And while we're at it, we'll actually need it slightly more general. So again, like a kind of normally for much of statistics and what you do with normal data science things, it's fine to stick to discrete or real valued continuous random variables with some density or so. There's one point where we need to go beyond that. So in the most general setting, a probability space has the following minimal requirements. Again, omega is some set of, okay, I called it points here, so elementary events, the things that can happen. And then we have to speak about more carefully, we can't do all subsets if omega is a continuum. So instead, we'll take what is called a sigma algebra, which is just a collection of sets with some properties. So these are all sets over omega. In the discrete case, just take the power set, but in general, you want a restricted set. We always need that the empty set is in there, and then we want that it satisfies closure properties. So whenever some set is in this set F, then we want that the complement set is in F, and any countable union of sets in F is also in F. So you can reason about what this kind of structure looks like, and that's the topic for a measure theory class that I'm not so interested in, so we'll just steal the results and don't worry about why they're true. What people might have heard of is the Borel sigma algebra. This is the solution for this problem in the continuous real case. If you have, say, omega all of the real numbers, or the real numbers between 0 and 1, then you can basically solve this, this question of what kind of elements can I look at, or what kind of sets of real numbers can I sensibly look at, by taking all the intervals, say the open intervals from some number a to b, and the closure under all these operations. And that turns out to be a well-defined sigma algebra. It has a name, and you can define probabilities on them. Why the whole thing? Well, in general, there's sets where you can show you cannot sensibly define a probability by designing them in a mean way. Again, this part of the theory is not relevant for us. So that's just listing the minimal requirements, and we'll be happy with those. Then the second bit, as before, we need a probability for all those measurable sets. That's what they're called here. Probability in general is a measure. Measure just means it's a function that maps sets to real numbers. And that also has some same properties as above in a way. But here it's only defined on this subset of sets. The solution for the real line is the Lebesgue measure, where you assign an interval its length, so the distance between the endpoints. And everything else, all the other sets in the Borel sigma algebra you can generate from these operations, you can also express their probability using these operations. One property here is that if you have a disjoint set of events, it could be infinite, but countably infinite only, then the probability of their union has to be the sum of the probabilities. That's for disjoint sets. Okay, is that questions up to this point so far? I mean, that's just the most abstract definition. It's a bit hard to show in a concise way why this is needed. I'll show you the example where we need more general probability spaces soon. Then based on that, a bunch of terminology. This will be repetition for sure. We have events. Events are just any of these sets that we can assign a probability to. They're called measurable sets in general. And this is just the requirement that we want something that we can assign a probability to. And straight from the properties, because we required them, this is all straightforward to show. We define the complement of an event as just the event that this event, the first event, does not happen. And that has the inverse probability. If we take the union of events that are not necessarily disjoint, then the sum of the probabilities is an upper bound. This is called the union bound. It basically just follows from the definition of sigma algebras, but it's a very useful tool in analyzing algorithms. Because here you have virtually no requirements about these sets. They can be arbitrary, they can overlap, the events can be dependent and everything. But we can still upper bound their probability. So we'll often use this to bound in an algorithm that something bad happens and that there's several ways in how something could go wrong. But if you can just have an upper bound on the sum of the individual probabilities for what everything could go wrong, that's an upper bound for having anything go wrong. Okay, so if we have some events, we can talk about independence. And this is really just defined via their probabilities. Events are independent if the probability is factor. So if you take the intersection that all these events happen at the same time, then that has to be the product of their probabilities. The usefulness of this definition is really that it doesn't need any intuition what independence means. It's a purely algebraic thing. You just check if the probability is factor. I'm not sure if we ever need this for infinite sets of events. I guess we do for sequences. So whenever we talk about an infinite set to be mutually independent, what this means is that every finite subset is independent. The mutually independent is important. There's weaker versions where you just say so here all the k sets together are independent, which means they're the intersection of all the events at the same time has to factor. You could also take, say, pairwise independence, where you only take two out of these elements and check if their intersection is the product of these two probabilities. That's a weaker notion. And you can say, in general, a k-wise independence. The higher the k, the more restrictive. And mutually means k is all of them. That sometimes plays a role. It's just important to not mix those up, but they're really an easy thing. So just again, pairwise independent would mean that for all I and j in our index set, I'm talking about the same events, A1 up to AK here. The probability for AI intersected AJ has to be the product of their two probabilities. But this does not in general imply mutual independence. There's examples, easy examples you can construct. I don't know. Do we need one? There was a cute one with the colors of edges in a triangle. So you color the edges uniformly at random in one or two of two colors, either red or blue. And then you ask whether, I think the vertices. And then you can ask for each of the edges, does it have two different colors at its endpoints? And if you take any two of these edges and you ask, are my endpoints colored in different colors, then these are pairwise independent. But if you take all three of them, they're not mutually independent, because if you know one color, you fix one color arbitrarily, and you know these two, then you know what the color is, and then the third edge is determined. So the events here would be A1, A2, A3. AI is at just two colors at endpoints. And then among this set A1, A2, A3, it's two-wise independent or pairwise independent, but not mutually. Okay, just a small example to make that point. You've probably seen some examples before. The last bit we can do with events is talk about conditional probabilities. And in the end, this all kind of just boils down to sets and subsets and kind of Venn diagrams. So the probability that A happens, given that we know that B happens, if you think of the events as some subsets, which really is what they are, if you know that B happens, right, then if in general the size of A was its probability, now it only becomes the size of A intersected B versus the overall size of B. And that's exactly what's written here, right? I guess I could all of B. And of course we have a problem here. If the probability for this event B is 0, conditioning on B happening sounds like a bad idea. It's algebraically certainly a problem, but also intuitively, if you think about this, you're betting on B to happen, and then you talk about how likely is it that A happens. If B has probability 0, this shouldn't make sense. Now, this is easier said than done, and sometimes could look very promising to condition on something, and then you find out it has measure 0, which is not always obvious. In the discrete case, it's obvious. In continuous cases, it sometimes isn't. Okay, last bit is the law of total probability. Is just a way of reformulating the definition, but it's often useful as a tool to compute things. If you want the probability for some event A, you can rewrite that as conditional probabilities involving some other events. Now, it's important that these other events form a partition of the entire space. And then the proof of this equation is completely boring. You just plug in the definition. But it's useful to think about it as a kind of case distinction. And whenever these conditional probabilities are easier to compute or evaluate, the law of total probability can help determine or compute things. Okay, last very important terminology, maybe not the last term, are random variables. So far we have set up the general universe, probability spaces. What are the things that we can sensibly assign probabilities to without running into paradoxes? And we've defined events, which are really the things that we can assign probabilities to. Things really get interesting once you talk about random variables, which are functions mapping these elementary events to some other universe. It could be anything. Oftentimes we think of it as numbers so that we can compute with these. And remember, I said earlier in our toy example here, for the die, this omega was just some more symbolic set. So if you define it like this, then you couldn't sensibly talk about say adding up two dies, but of course we could map all those to numbers. So we could have x is the mapping to 1 to 6. In the natural way, you just count the dots. What did I do? And that way you can talk about the numerical value. Okay. So boring example of a random variable. Think of it as a random variable can throw away information, and then it can become a more versatile tool. It could say we could also have y, which maps this just to even and odd in the usual way. That's another random variable, not mapping to the real numbers, but yeah. We'll see many examples where this will become clear. Now we have a new type of event, namely that a random variable has a certain value. With the obvious definition, it's the set of all primitive events that map to the right value. And we can define, so this was going from a random variable to an event. We can also go the other way around, from an event to a specific random variable, which is the indicator, just saying yes or no, 0 or 1, does this event happen or not? So again, this is this Iverson bracket, which is 1 if the event happens, if omega is in A, and 0 otherwise. Okay. Then we can define a few terms. Most of these you'll have seen. So if you have a random variable x, and this is some real number here, or at least something where it makes sense to talk about less or equal, you can define a cumulative distribution function as just the probability that this is below a certain value. If x is discrete, then necessarily also the range you map to will be discrete. For a continuous random variable where you start with something that's not discrete, you could map it to something discrete, or you could map it to something continuous. And if you map it to right, okay, that's still for the discrete case, you can define the probability mass function. It's just for all the values in your universe here, suppose that's discrete. So if say that calligraphic x, that's an h, is the natural numbers, then you could define something like this. Just the probability to have a certain value, and that completely describes the probability distribution, the random distribution. If you have some continuous random variable, you can still define this cumulative distribution function. And it's often useful if this is smooth enough to look at the derivative instead. And the derivative of the cumulative distribution function, if it exists, is the probability density function. That's again things you'll have seen. The standard way to deal with most continuous random variables. And a slightly non-standard piece of notation is this equals with a d above it. which I'll use to denote that the two random variables on the sides of the equality have the same distribution. Formally, it just means that their CDFs are the same. There's many ways people use notation for the same thing. I think it turns out to be very convenient if you combine random variables. Now you can say x is equal in distribution to y plus z. And if these are mapping to real numbers, it's clear what that means. But it's a fairly sophisticated. If you express this via the distribution function, you're already talking about some convolutions and so on. It's a nice way to express what we want here, equality in distribution, without requiring special notation for standard operations. All right. We've talked about independence for events. You can also talk about independence for random variables. The way to think about this is random variables here, they can map to any kind of set X. Often we'll think of that as real numbers, but it could also be multidimensional. It could be mapping to R to the K. And then we can, for this vector X, the vector random variable, we'll just call these functions that we just defined the cumulative distribution function, or the probability mass function, or the probability density function. We call those the joint versions. And we can look at individual components of the vector and then look at the marginal distribution of that, or the marginal functions. And now a set of random variables, or a collection of random variables, is independent if their joint distribution, their PDF or their PMF factors. For example, X and Y are independent if the probability that they together have the certain values, so X, capital X is, the random X is equal to X, random Y is equal to some Y, that has to factor into the probabilities of the two events. It seems like it's the same thing as for events, but I guess formally it isn't, but it naturally follows. And this is, I guess, for discrete, you can do the same for the probability density function, and it does the right thing. Okay, here's an important bit. That's what we'll come back to many times. IID sequences of random variables. IID stands for independent and identically distributed, and the independent stands for mutually independent. Nobody says that, but it's implicitly there. So this is often the starting point of some theorem. You have an IID sequence of random variables. Maybe they're all fair coin tosses, so heads or tails, or 0 or 1. But you have an infinite, countably infinite number of those, and then you can work on from those. So that's just what that formally means. Okay, I guess I lied earlier. This is another important term, the expected values, but you'll have seen about this. If you have some random variable, you can take its expectation. And for this, really, you need to be able to map. This only works if you map to some number or something where you can compute, because here you're taking sums of values that X can take. Of course, the definition of expected value of X is the sum of all possible values times their probability, if that's the discrete case. If you have a density, then you take the integral. It looks very similar to the sum case. I guess it's nice here. Shows the analogy. You can also define this in general set measure theoretic terms, where now the integral becomes a Lebesgue integral. We won't actually need that, so I think we don't need to talk about it. It could happen that a random variable does not have an expectation. Whenever that sum or integral doesn't converge, then it just doesn't have a random, well-defined expectation. That can happen. Okay. Important properties of the expectation are just following from the definition. Remember that it is a sum or an integral, and these are linear. So If you scale a random variable by multiplying its outcome by a constant factor, the same will happen to the expectation. If you add up two random variables, the expectation of the sum is the sum of the expectations. You know this, but it's good to keep in mind. And as an important special case, if two random variables are independent, then their expectations factor. This again follows directly from the definition, but you need to do the math, I guess, to see it. If you can factor their probabilities, then you can split away the sums, and it becomes the product of two sums. Note that here this doesn't imply the other direction necessarily. Don't know if there's a nice. There's certainly an example, but not one I can come up with now. Conditional expectations are a slight twist on what we had before. It's essentially the same thing. You just take, whenever you had probabilities before, you now take conditional probabilities. Yeah, conditional expectation for an event, I think this there's an x missing here, right? Should be multiplied by x. More important is the conditional expectation, where you have take the expectation of some random variable, and the event that you condition on is another random variable having a certain value. This often pops up, so it's worth mentioning as a special case here. And if x and y are discrete, the obvious definition works. Just replace the probability for x having a certain value by this conditional probability. If x and y are continuous, then in general you have to be careful with these kind of statements, because you're conditioning on an event of probability 0. If you have a continuous random variable, that the probability that it takes one specific value, the measure of a point set, is usually 0. But you can still sometimes define things via densities. So if you have two continuous random variables, x and y, with a adjoint density function, then you can define the marginal density of y by integrating x out. So just what it says here, you take the joint one, you integrate over the entire domain of x, but you keep y as a variable. And then you can define this conditional expectation properly using this marginal density. If you just go from the definition up here, you would be conditioning on an event of probability 0. And so this would not work. But if you have densities, you can give a sensible definition to this conditional expectation here. The last thing I want to point out here is if you have some conditional expectation of either kind, discrete or continuous, you can actually turn that into a new random variable itself. So first of all, if you fix the value of y, the little y, you fix the value that you condition the random y to have, then that's a function. And now you could say I'm taking one random variable, I'm applying a function. That's just composing two functions. That's again a random variable, g of random y. And so we can denote this by this. But this notation, as widespread as it is, you should keep in mind it really stands for one of these two things. And for example, if x and y are continuous, but they don't have a nice density, it might not make sense to write this. Could be not well defined. But if it's well defined, you can use the law of total expectation, which is expressing some expected value by averaging over y and then inside taking the conditional expectation. That's one of my favorite tools, because sometimes you can evaluate a hard to compute expectation by first conditioning. It's a bit similar to the law of total probability. that can be a powerful tool. All right. Pinky promised last slide on this, some famous distributions. There's no esoteric ones, you'll know those. I just wanted to have the notation somewhere written. So just a B with P will be the Bernoulli distribution. It's a biased coin flip where P is the probability for having a 1 and otherwise it's 0. Then we have the binomial distribution, which is the sum of n such coin flips, where n and p are parameters. Then we can have the discrete uniform distribution. That's what the die was. So our random die, again, the random die has uniform distribution between 1 and 6, the obvious way. Let me just write this sloppily like this. Another thing that pops up is the geometric distribution, which is you have some coin with a probability p of coming up as a 1, and you have now you keep flipping until it shows a 1, and the number of coin flips you needed in total is the geometric distribution. Okay, the only continuous distribution that I'm using for sure is the uniform distribution. For example, over the unit interval. There's of course many others, but I don't think we need any of them.